The main goal of the University of Vienna is to integrate all the different aspects and all the different technologies which were developed by our consortium partners. So, for example, Single Quantum focuses on the detection part. So they developed superconducting nanowire detectors, mainly for photonic applications, but in our case for molecular detection. We validate these geometries with respect to their efficiencies of to detect these molecular ions or neutrals later on, and then they can build on this feedback and play with the different geometries, and then we can find the optimal solution for this task. Then we have the University of Basel. They prepare photocleavable tags to control the charge state of the molecules, and there we also validate these tags with respect to their efficiency. How efficient is it to produce a neutral molecular beam? We currently try to start with ions. So we prepare a charged molecular beam with commercial methods like electrospray ionization, matrix-assisted laser desorption. Then we neutralize it with one tag at a specific wavelength. And then we have a second tag which is attached to the molecule and which can be addressed by a different wavelength. So, for example, you start to cleave one tag off with 532, you get neutral, the molecule flies on, and then you detach another tag at 355 nanometer, and you produce an ion again. So you basically just neutralize your molecule and post-ionize the molecule. The first stage, we have our source part, is concerned to bring the molecules into the gas phase. And there we have different sources. So on one side, we have sources for proteins, then we have sources for neutral atoms, we have sources for metastable atoms, and we have sources for a noble gas ion. After the source part, we have a quadrupole, which allows us to mass select a specific mass to charge state, which is needed to study the photocleavage mechanism. Then, after the quadrupole, we have a buffer gas cell. So this buffer gas cell, you can just imagine it's a cell filled with noble gas like helium or argon. And in this cell is also a hexapole to guide the different ions through the setup. And this buffer gas cell is, when switched on, helps to cool the molecules internally and focus them on axis, so reduce the transverse velocity spread. Then a bender chamber. And in this bender chamber, we have a DC guide and a bender, which allows us either to deflect the ions or let them pass straight through. And if they pass straight through, they enter a time of flight mass spectrometer. There you can really analyze the mass to charge state of the molecules with high precision. And if you deflect the ions, you can just guide them towards the SSPD where they are detected. With this method, we already detected insulin. It's a class of material, so to say, that isn't investigated at all in literature. So, of course, if you have an ion or a neutral, it makes a difference. So the particles or the molecules will have different properties because of their charge state. It would be really interesting to have on one side a continuous high flux neutral source, also for interferometry, and also have on a detection, develop more on the detection side.